Good morning. We are going to discuss about the blade flapping dynamics. If you remember, in forward flight, we saw that the wind velocity depends on the azimuth. We saw, in fact, that the blade which is advancing has a velocity of hover tip speed plus the velocity of the flow, and the blade which is retreating has a velocity equals with the hover tip speed minus velocity of the flow. It follows that this inequality in velocity distribution will cause the helicopter rolling. That was observed by Sierva. In order to cope with that, the flapping hinge was introduced. In this way, the blade has the freedom to move up and down, and this inequality of velocity distribution will disappear and will be displaced by an equality in lift. We are going now to derive the flapping motion of the blade. The assumptions that we are going to make are the following. We assume that we are in a forward flight. There are central flapping hinges without springs and a stiff blade. No blade twist and a constant chord. We assume small flapping angles, linear aerodynamics and no stall effects. We assume a constant RPM. We consider that we are in a control plane. What is the control plane? If you remember, we were discussing about the tip-off plane, and we defined the tip-off plane as the plane formed by the blade tips. We used this plane for power calculation. However, one can use also the shaft plane as a plane of reference. The shaft plane is the plane perpendicular to the hub, but there also exists the non-feathering plane. The non-feathering plane is the plane where an observer sees no variation in cyclic pitch. The control plane or the swash plane swash plate plane is the plane which contains the swash plate. As we are dealing with the flapping motion, we are going to study this in the control plane. Assume the blade rigid and assume that is flapping with an angle beta. Consider a blade element of mass dm. The force is acting on this blade element R, the gravity G dm, the lift force as we are in hovering flight dl, and the centrifugal force, which is actually 20 times higher than the lift force and equals with dm omega squared r cosine beta. R is the radius of the blade of this position. The equation of motion then of the flapping blade is the blade moment of inertia multiplied by the blade acceleration equals with the summation of the moments acting on this center. What are the moments with respect to this center? First, the aerodynamic moment, DLR, which can be integrated along the radius. The centrifugal moment, which is the centrifugal force multiplied by the arm, R cosine beta, and the gravity moment, which is actually gravity force multiplied by the arm, R cos beta. For a normal rectangular blade, the blade moment of inertia can be easily calculated and equals with blade of the mass blade r squared divided by 3. Now, if we are going to look at this equation, usually the gravity is neglected as it is quite a small force. We make the small angle approximation and the sinus of beta equals beta, cosine of beta equals 1. You see then easily that the blade flapping equation for a blade in hover equals with beta double dot plus omega square beta equals with the aerodynamic moment divided by the blade moment of inertia. Well, if you see this equation, it calls you back that actually this is the motion of one mass which is hanged on a spring and a damper. If you recall this differential equation that you learned in the beginning of the study, you see that the natural frequency is omega n and equals with the spring divided by mass. For us, it means also that the natural frequency of the flapping motion equals with the RPM of the blade. Is that good or bad? We will see later. How is actually flapping influencing the blade angle of attack? The idea is that if the blade is flapping, actually, the advancing blade is having a velocity beta dot r, and the retreating blade is having also an opposite velocity beta dot r. On the advancing blade, actually, if you look at the angles acting on the blade, the beta is increasing, the flapping is increasing, the angle of attack is decreasing, so the lift is decreasing. On the retreating side, the flapping blade is decreasing, the angle of attack is increasing, so the lift is increasing. In this way, we can counteract the inequality of velocity distribution. Now going back to the aerodynamic moment. For a hovering helicopter, the aerodynamic moment can be quite easily derived. We have just to perform this integral. Recalling the definition of the lift, we see that we have to know the angle of attack of the blade and the velocity of the blade. In hovering flight, this is mostly approximated as omega r. Now, the angle of attack, if you look at this figure, it is pitch theta minus the inflow angle. But now, this inflow angle is the tangent of Vi plus beta dot r divided by omega r. We make the notation of inflow ratio, which equals the induced velocity divided by omega r. In this way, we can decompose the aerodynamic moment in three integrals. One integral depending on the pitch angle, one depending on the inflow ratio, and one depending on the beta dot flapping velocity. Each integral can be easily performed as the values are constant and not depend on the radius. The log number is another important design parameter, which is actually a measure of the balance between the aerodynamic forces on the numerator and the inertial forces on the rotor on the denominator. It takes values between 5 and 16. In general, log number has a value between 8 and 10 for articulated rotors, so the rotors which involve flapping and lead-lag hinges, and it is lower for the hingeless rotor, between 5 and 7. Now, going back to the aerodynamic moment and performing the integrals, the three integrals that we were discussing, we see that we obtained the aerodynamic moment as depending on the pitch angle of the blade, on the induced velocity of the blade, and on the beta dot flapping velocity. Actually, this last term is an aerodynamic damping term. And now, substituting the aerodynamic moment into the initial flap equation leads us to the final form of the flapping equation for a hovering helicopter. Beta double dot plus aerodynamic damping gamma over 8 omega RPM flapping velocity plus the centrifugal spring omega square beta equals with external excitation. So this is also the equation that we know of an mass which is moving on a spring and with a damper. The solution of the flapping equation is of course an homogeneous solution plus a particular solution. The homogeneous solution can be easily expressed and depends on a flapping amplitude and of course on the omega of the RPM of the rotor. And the particular is the solution which corresponds to the particular to the free term in the differential equation. If we would represent the transient flapping motion, we would see that it will damp very quickly. For example, if you represent here the azimuth of the blade, and if you represent the solution of the homogeneous solution divided by the amplitude for a helicopter with a log number 6, you would see that the transient flapping motion damps very quickly and the blade aligns in a flat plane, which is the tip-off plane. What is the interpretation of the aerodynamic flapping contribution? The aerodynamic forces are actually damping the motion. You see that if I have a perturbance of a flap velocity beta dot, there is an increase in delta alpha, which results in a change in a lift force, which results into a flapping moment, which is actually having a minus, showing that are damping the motion. And now, the blade responds to 1 per rev excitation. Consider now that we have a vertical gust acting on the as external excitation with a term of cosine omega t. It follows that the blade is excited at resonant condition because the flapping natural frequency equals with omega RPM of the rotor. Now we have a resonant condition. Is that dangerous for the helicopter? Well, as long as we have damping, it is not dangerous. If you would represent this damping of the helicopter and as a function of the forcing function non-dimensionalized by the natural frequency, you would see that as the gamma is, the log number is increasing, the amplitude will decrease much. So in the range of log number, the damping is between 30 to 90%, and there is no danger for resonance due to the strong damping. The phase of the flapping motion, as we are at the resonance, it follows that the phase is 90 degree, and we are always, if we flap in one, the response of the blade will appear 90 degrees later. Conclusion. Applying a 1p disturbance, the flapping motion, it will grow automatically so large that the aerodynamic damping will just cancel the applied aerodynamic moments. Therefore, the blade structure has nothing to do to react to the important 1p excitation. This ends the first introduction into the flapping dynamics and its characteristics for forward flight.